In this lecture, we're going to look specifically at the Australian Standard 1100 Drawing Standards. Before we start, we just want to recap and talk a bit about working drawings, orthographic, and third angle projection. Now, we discussed this to some extent previously, particularly working drawings, but we need to go into this to a greater extent. So we're going to develop our understanding particularly of orthographic and specifically third angle projection. So working drawings. Working drawings are also known as orthogonal drawings, but can also be referred to as workshop or cabinet drawings. And they're used by a production team or an individual to construct a project. They consist of systematically arranged views of the faces of an object, such as the front, top, and side views. However, more views may be used to show additional details as necessary. Working drawings may be drawn by hand, and in the past they always were drawn by hand, but today they're increasingly produced by CAD programs, and you'll be working on that in the tutorials as well. So working drawings are a two-dimensional representation of a three-dimensional object. All working drawings will contain similar kinds of information presented in a consistent way. AS1100 is an extensive set of standards that ensures that designers, engineers, etc., anyone who needs to, to be making things, know what the rules are to ensure a significant degree of consistency. And I put rules there in inverted commas because they're not strict rules, they're guidelines, but they're fairly, strongly adhered to because this is a visual language, and these are the rules that define the visual language. Now, before we start investigating these rules, we need to ensure that we've got a sound understanding of what orthographic projection is, and specifically what third angle projection is. So we're going to just discuss that a little bit now. Orthographic projection, so sometimes referred to as orthogonal projection, but also is referred to as, working drawings. So the three are related very closely to each other. So it's a means of representing three-dimensional objects in two dimensions. It is a form of parallel projection. So if you look at the image there on the right-hand side, you can see there's a three-dimensional object there, and that is how it will look in a two-dimensional orthographic representation. So you've got your front view down in the bottom left, you've got your top view directly above it, and then you've got your right view directly to the right side of the front view. Now, in most working drawings, only three views are usually required: the front view, the top view, and the right view. And that's specific for third angle projection, which we'll talk about shortly. Generally, the front view is determined as the view that has the most detail. However, when generating working drawings for timber design projects, such as a sideboard, for example, the front of the sideboard will correspond with the front view in the working drawing, as it could otherwise be confusing. Now, the other thing, just as a point of discussion, in this example here, we're using the right view. When we're using third angle projection, there is always a bias towards the right view. But say, for example, if in this drawing here, there was detail on the left-hand side or the left end, we would have to have an additional view in there as well. There are 6 principal views in orthographic projection as highlighted in the image adjacent. So you can see in the image, you've got your front, top, bottom, left, right, and rear. It kind of makes sense. As already discussed, most working drawings used third angle projection will include a front view, a top view, and a right side view only. Additional views are added if there is unique detail that can be communicated only by the addition of that view. And if you think back to the previous lecture where we were looking at the case studies, and there was the cabinet which had the curved legs, and in that case they included a bottom view as well because there was detail that was very specific to the bottom of that project. Now sometimes it can be confusing, particularly when you're trying to explain it to students how the different views are achieved. And so I've put this little animation in here to kind of illustrate how it works particularly for third angle projection. So one way of looking at it is to imagine that the object that you're drawing, it could be the sideboard, it could be a car, it could be whatever, is enclosed inside a glass cube. Each face of the cube represents one of the 6 principal views. As the viewer looks through each specific face, what they can see through that face becomes the 2-dimensional representation on the page. So it kind of makes sense when you're looking at it from the front and you can see what you actually see projected onto the front. And when you move over to the top, you can have a look and see what is projected on the top. And when you go and have a look at the bottom, or the left side, or the right side, or the rear, you can see what is projected on those views. Okay, so now let's just have a quick look at third angle projection. So working drawings produced under AS1100 use third angle projection. Some other countries' drawing standards use first angle projection. Now, it's not necessary to delve deeply into the difference, as everything demonstrated thus far relates to third angle projection. And the reality is, if you're operating in Australia, we're always using third angle projection. It's just that you need to be aware. So if you come across drawings that have been drawn in other countries, it's more widely used in England, first angle projection, and parts of Europe. Just so you can understand how to interpret those drawings. So the adjacent images illustrate the difference in how the principal views are achieved and laid out on the page. So when I was talking before about, think about it from the point of view of a glass cube, where it gets a little bit weird with first angle projection is it's kind of projecting views onto a screen behind the project. So for example, looking at that top image there, if I wanted to look at the right-hand view, it's actually represented out on the left-hand side of the object. So that's kind of where it can get a little bit confusing, and that's why I don't want to go into first angle projection to a great extent, because we don't use it. Whereas you can see again, there's another image there of third angle projection, and it shows that concept of the invisible cube, being the images being projected onto the faces of the invisible cube. Now, importantly, all working drawings must contain a projection symbol. Therefore, all working drawings using AS1100 must contain the third angle projection symbol that's shown here in both acceptable forms. So you can have it, one of those symbols down below there, you can have it facing one way or the other way. They are the acceptable forms of that symbol. Okay, so now let's get into the nitty-gritty of AS1100. Engineering drawing is the main method of communication between all persons concerned with design and manufacture of components, building and construction of works, and carrying out engineering projects. The practice of drawing is in so many ways so repetitive that in the interests of efficient communication, it is necessary to standardise methods to ensure the desired interpretation. And that's a quote that's come from a very respected engineer. AS1100 is an extensive document. The section from which the following information or discussion in this lecture is drawn is over 240 pages in length. Over the next few minutes, we will cover the barest minimum necessary to assist you and your students to present drawings to an acceptable standard. And the other thing that I would put in there as well is to say that I'm doing this from a timber perspective. So there is a whole lot of information in AS1100 that might relate to, threads, or, how do you represent welds, or, tolerances and all sorts of things like that are not really relevant for working with timber. So I've kept that out. Now, the main areas we're going to be focusing on are scale, setting out views, dimensioning, line types, lettering and numbering, title block, and material lists. Scale. Drawings need to be accurate and drawn to scale. For example, if you are drawing a car, it obviously would not fit on a sheet of paper. So you would reduce the drawing size to around 1/20th of its actual size. And that does depend on the size of the paper you are drawing on. If you are drawing a chair, it might need to be around 1/10th of its actual size on the paper. A small box might be drawn life size. And of course, again, it depends on the size of the paper. Now in schools, A4, A3 and A2 are probably all that we will encounter. Anything larger than that is really, for the professional engineer or designer. Now, every drawing must include its scale clearly printed so the reader knows how big the object will be when it is completed. On a scale drawing, every part must be equally reduced or equally enlarged, but all dimensions are shown in actual size, as they exist on the real-world product, and always in millimetres. Now, the same scale is not always used for all drawings on one sheet. So you might have to have a blow-up or a detail drawing on there. So where you're drawing details to a larger scale, you need to clearly indicate it. Now, choosing a scale. So the most common reduction ratios are 1:2, 1:2.5, 1:5, and 1:10. These all easily divide into 10, which makes it easier to convert real-world measurements when drawing. The next most common reduction ratios are 1:20, 1:25, 1:50. Now, full size or life size is always 1:1, and a drawing larger is 2:1, 5:1, 10:1, etc. Now, when you're choosing a scale, it's important to ensure that there is enough space on the paper for each of the required views, as well as dimensions, annotations, and other necessary information. Now, you can see, just when you're looking at this image here on the right of a working drawing, that particular student there has chosen a scale of 1:15. Now, even though it's not a common scale, it is one that is easily divided into 10. And they've done that because they've wanted to kind of get the right balance of their project on the page, but still leaving enough space for annotations and dimensions. Setting out views. Now, we've already discussed this to some extent. In most cases, a front view, top view, and side view are necessary. Third angle projection requires us to, in most cases, use the right side view as shown opposite. Now, that working drawing that's shown opposite was produced by a secondary student, and the work is of very high quality. However, there are a number of areas where the student has not complied with AS1100 standards. After you have completed this lecture, review the working drawing and identify at least 2 errors. The three views must remain in perfect alignment with each other. When drawing by hand, the front view should be completed first, and then like construction lines can be projected upwards for the top view and outwards for the side view. Dimensions in millimetres should be positioned neatly away from the drawing itself. The image adjacent is a good example of how this could be presented. Now in this case, the mallet has a little bit of additional detail from the left-hand view end. So in this case, there is a front view, there is a top view, there is a left view and a right view as well. Now we'll look at dimensioning. Orthogonal or working drawings must include all the necessary measurements so that the object can be created from the information supplied. Avoid repeating the same measurement in another view, it is unnecessary. The main drawing should be easily viewed and uncluttered, with dimensions clear of the drawing whenever possible, preferably to the outside edges of the views. Dimensions between the views should be avoided wherever possible. The adjacent drawing contains an error in this regard. The drawing of the mallet opposite contains a number of errors. They're only minor, but a number of errors or methods that are not best practice. After you have completed this lecture, review the working drawing and identify at least 2 errors. Regardless of the scale used, always use the full size measurements on the drawing. All dimensions should be oriented so they may be read from the bottom or right hand side of the sheet. Dimensions should be expressed in millimetres, although it is not necessary to write the symbol mm after every figure. A general note, such as all dimensions are in millimetres in the title block, is sufficient. Additional conventions relating to dimensioning are indicated in the adjacent image. Now, I would recommend that you spend a bit of time looking at this image because there is a lot of information here, particularly about how arrowheads are drawn, how dimension lines are drawn. The projection lines go 2 millimeters past the dimension lines and there's a 1 millimeter gap. The arrowhead should touch projection lines at extremities of the dimension. And spacing between dimension lines and outline should be equal and about 12 to 15 millimeters apart. Where a number of parallel dimensions are close together, they should be staggered to ensure clear reading, as shown in the adjacent examples. And again, there's a fair bit of information there. Line types. Now, I've really summarised this quite a lot because AS1100 has extensive information about line types. So just understand that this is a very, very abridged version. There are 5 types of lines common to orthographic drawing. Construction lines are very faint lines used when setting out the drawing. They should not be easily visible, so there is no need to erase them later. And obviously that's on the assumption that it's being drawn by hand. Outlines are a continuous thick line, and that's what I mean by that is 0.5 millimeter thick, used for visible outlines of objects. Dimension, projection, and leader lines, which were discussed to some extent on the previous slide, are all thinner continuous lines, about 0.35 of a millimeter thick, and they assist in reading the drawing. They are normally kept outside the actual drawing itself. Dimension lines have an arrowhead at each end that touch projection lines and illustrate exactly where measurements start and end. Projection lines are parallel lines that project from the drawing, not quite touching the drawing. It was a 1 millimeter gap as specified previously, at the 2 points being measured. Leader lines are links from printed drawing, and they're not quite touching the drawing, at the 2 points being measured. Leader lines are links from printed information to the drawing, usually with an arrowhead touching the specific part of the drawing. And have a look at the next slide. So the question I would have with that first image there on the right hand side, where is the leader line? Hidden detail lines are used for outline detail that cannot be seen because it is behind something else in a particular view. It is a line of dashes and a light line. Center lines are a thin series of dashes, alternating long and short, that represent the middle lines of an object, like the side view of a hole or tube. When looking into a hole, use horizontal and vertical center lines crossing in the middle, which are then used to dimension a location on the drawing. And examples of both can be seen in those images adjacent. Lettering and numbering. When using A4, A3 and A2 paper, always print using uppercase. The recommended minimum height for letter sizes are between 5mm and 7mm high for titles and drawing numbers, between 3.5 and 5mm high for subtitles, view headings and heading descriptions, between 2.5 and 3.5mm high for general notes, material lists, dimensions, etc. And you can see examples of that down in the bottom right hand corner. The title block represents the general information source for a drawing. It is normally placed in the bottom right hand corner of the drawing frame. The following information should be provided in the title block, and again, see the adjacent image. The name of the firm for whom the drawing is made, the title of the drawing, for example, the official name of the drawn object, the drawing number, which represents the unique identifier of the drawing in the file, the scale of dimensions, the angle of projection used, either in words or by symbol, and you can see the symbol there, the signatures or initials of the draftsman, checker, approver, and issuing officer with the respective dates when each completed their work on the drawing. Now, in reality, in the school context, you're probably not going to have those. And you also then need other information that relates to dimensions, tolerances, drafting standard used, which you can see there, material, surface finish, paper size, tool and gauge references should be included in the title block, as well as any other data which may be of importance to the drawing. Now, some of those things there would relate more to the engineering side of the drawing, but it's just good to know. Now, material or parts list. So when a drawing includes a number of parts on the one sheet, or an assembly drawing of a number of parts is required, a tabulated list of the parts is attached to the top of the title block and against the right hand drawing frame as shown adjacent. Now, the list should provide the following information, and this is generic information. The item or part number, such as the letters on the mallet. So I've included the mallet drawing there because it shows that there's two parts. There's part A and there's part B. The part name, the quantity required, the material and its specification. And in the case of working with timber, that's specifically length, width, thickness, the drawing number of each individual part, other information as considered applicable. So you'll see here, this is a very basic parts list for a simple timber project, and it could look exactly like this.